on this computer. Okay, and I'm going to open the chat up here. There it is. All right, I'm going to move this over a little bit. Okay, could somebody chime in on the chat room? Make sure that's working, please. Okay. Okay, and it looks like you can unmute yourself now, so that's good. All right, great. The Zoom is working. People can hear me. That's great. All right. Some administration stuff. I talked to Top Hat. And so because of the way we're doing the homework, all of the homework is now available for review, okay? Now, that means that in chapters 12, 13, 14, and 15, and 16, there aren't any additional review homework questions. There's just going to be the set of homework questions, and those should be representative of what we see on the exams, although not exactly the same question, of course. So what'll happen is you get to do the homework and it gets graded at noon on Fridays, and then after that you can review it, for example, for our upcoming final. So I have the only one that won't be reviewable after noon on this Friday is the homework for chapter 16, which is polymers. Okay, so that's the only one, and I've actually have that, so it's graded on Wednesday, next Wednesday at noon, and therefore you have over 24 hours to use that chapter for review before the final at 2 p.m. on Thursday. Okay, so you should be able to go back to Top Hat and see all of the homework questions are available for review, and you have infinite attempts, so that you can, try to figure it out. If you can't figure it out, go ahead and submit a couple times, and then you should get to the correct answer after that. Okay, so that's a win for many of you who are asking for this. Overall, there is a participation grade in Top Hat, but I wouldn't look at that as your total participation grade. Some people are asking about it. The participation grade on tracks is a total of 80 points, and part of that is, did you come to some of the lectures? Did you participate in the activities? Did you, do all of your homework? All those counts toward participation. So please don't worry about that grade yet, but you'll see that happen really on the last week. I'll probably put it in after our review on Tuesday, and then the only grade left would be the homework grade for chapter 16 and the homework and the final grade. So I'm hoping to have all that in, so you have a really good, enthusiastic reason to study for the final. Excuse me. All right. So what I'm going to do now is, if there are no questions about administration, I would like to move on with chapter 14, goal 2. Okay. Will we be able to use any notes for the final? No. Unfortunately, I'm writing the final such that we will use just that blank sheet of paper, your table of periodic table of elements that's blank. Everything else should be just things that you should be able to figure out or already know from what we've done. It's not, I'm not going to make you do a multi-step 7-part synthesis or anything like that. We're just going to keep it, individual simple questions about one topic at a time. Okay? So that was a question in the chat there, by the way. All right, let me go ahead and move my mouse over here so I can share my screen. Nope, that's not what I wanted to share. All right, we should be seeing my screen as chapter 14. Let's see. All right, we even get movement here. Okay, this is chapter 14, carboxylic acid derivatives. we did something about the nomenclature and properties yesterday. Now we're going to do reactions. And so these are all the different reactions, how to make these derivatives, and some of the reactions the derivatives have. Okay. So the first thing we want to do is that we want to look at the acid chloride and the reaction it does. When we created that acid chloride, the chloride derivative of the carboxylic acid here, right here, that made our chlorine a better leaving group than the OH, which makes it more reactive. That means that it reacts very rapidly with things like alcohols or anything that had a Lewis acid or a pair of electrons here. Those electrons come in, attack the carbonyl, and then kick the chloride out as an ion. And when we do that, we can then also lose the hydrogen to some other Lewis base in the solution, and we create an ester. So if we take our acid chloride, react it with an alcohol, we typically use a little bit of base just to pull away that acid, but it drives the reaction toward the ester. So this is that first step down. We go from the most reactive chloride down to an ester, okay? So, and let's see. The second way to get to an ester is we can actually take one ester we already have and react it with an excess of another alcohol in the presence of an acid catalyst, and we can convert one of those alcohols will displace the other one. The same thing happens. We have one alcohol acting as the Lewis base, attacking at the carbonyl, and then we have an opportunity to lose that alcohol that attacked or the alcohol that was already on the ester. If we lose the alcohol that's already on the ester, we end up what we call transesterifying. We're converting one alcohol from the other, so we're transferring alcohols. So it's a transesterification reaction. Okay. This typically works with acid because we protonate the leaving group, one of the alcohols, to help it be a leaving group. Also, one of the things that really helps drive this is, notice that this is methanol. The leaving section here is methanol. Methanol has a very low boiling point. It only boils around 55 degrees Celsius, which means that if we heat this reaction up, we can drive the methanol off, driving the reaction to completion. That's one of the driving forces for these transesterification reactions. Okay, so that being said, amides, which are the functionality with the nitrogen in here, are actually not reactive toward alcohols, okay? So I showed you that acid chlorides react with alcohols to make esters, and esters will react with other alcohols to create esters, and even in hydrides. And hydrides are even more reactive, somewhere right here in the reactivity scale. It's in between acid chlorides and esters. And they'll react with alcohols to give esters as well. However, the amide does not react. The nitrogen is a stronger nucleophile, and that makes it a stronger base. And so the reaction does not occur. Oxygen is not strong enough to displace the amine of the amide. So notice that, we have chloride being displaced by oxygen here, oxygen being displaced by oxygen, oxygen being displaced by oxygen. Here, the amide does not react, no reaction, because the nitrogen is more basic than the oxygen, and therefore that reaction does not occur. Excuse me again. So let's try to look at some reactions on how we actually form amides now, okay? One of the great ways to form a primary or secondary amide is just to use an amine, a regular amine or not. To get to the primary amide, that's just with one carbon bond here, we must use ammonia, okay? So ammonia has no carbons on it. It comes in with it as its Lewis base, comes in and attacks our carbonyl, kicks out chlorine, and an equivalent of something else that has a protein. Notice we have to use two equivalents of ammonia. The reason we're using two equivalents of ammonia is one equivalent is actually attacking the carbonyl to give us the
Sorry, I had to move something out of the way here. The first equivalent attacks the carbonyl and gives us the amide bond. The second equivalent sucks up any of the HCl produced from the reaction. So notice we have one equivalent of amide and one salt of ammonia and HCl. So that's an important feature of this. But again, we have acid chloride being the most reactive species. We've shown that it can react with alcohols and it can react with amines to create esters and amides. So, all right, somebody asking a question? Okay. All right. So we can also react anhydrides with ammonia to form primary and secondary amines. For example, if you react an anhydride, remember that's just with like two carboxylic acids kind of tied together here, right here. One equivalent is going to be used to react with the carbonyl to create the amide, and that's going to produce a carboxylic acid. Now that carboxylic acid is acidic enough to react with ammonia, therefore we need to give us a salt. Therefore we need two equivalents of ammonia when we react anhydrides as well, okay? We needed two equivalents of ammonia to react with the acid chloride because we produced HCl as an acid and it had to neutralize it. In the case of an anhydride, we have produced an equivalent of carboxylic acid as well, which is also going to be neutralized by any base. Therefore, for both the acid chloride and the anhydride, we must have two equivalents of an amine. Okay, now let's react an ester. Okay, so acid chloride is the most reactive, anhydride's the next most reactive, esters are the third most reactive. And we know that we can take an alcohol and displace an alcohol with that, but we can do the same thing because our ammonia is acting as a Lewis base right here. We have our lone pair coming in and attacking here and leaving as a neutral alcohol, okay? So the key here is you only need one equivalent of the amine because you're producing a neutral species that is not an acid. Therefore, we do not need that extra equivalent to balance that out, okay? So once you have an amide though, it will not react with any other amine. There's no driving force to get it to displace. So once you form the amine, it typically is very stable as the amine you formed. The amide you formed, okay. So let's go back to that interconversion table here. So like I said before, the one up here is the most reactive, the acid chloride. And you can use the acid chloride to make any of the other derivatives, okay? For example, if you took an acid chloride and reacted it with a carboxylic acid salt, you can actually form the anhydride. Now you can take an anhydride and use it to create any ester or any amide, or if you reacted it with water and base, you'll actually get to that other system here. And again, once you have your anhydride, it's more reactive, so you can't go back. You can't go from an ester to an anhydride. You can't go from an ester to the acid chloride, okay? So that's kind of a key feature in this table, looking at this table, is that once you have your acid chloride, you can make anything from it. But let's say you already have an ester, well, you can only hydrolyze it down to your carboxylic acid or make an amide out of it. And that's about all you can do with it. So that's really important when you're trying to figure out which reaction to do first in a series of reactions, okay? So let's look at a couple other reactions that are not just converting from one functionalized group to another. And when we looked at this reaction in a previous chapter, we used that Grignard reagent, that negatively charged carbon, right, to attack other carbonyl compounds, okay? So we can use that same Grignard reagent, that negatively charged carbon as our nucleophile. However, it reacts a little bit differently, okay? The first equivalent of our Grignard reaction would actually create an intermediate that is not, that would also have a carbonyl functionality on it. Therefore, notice we use 2 equivalents of the Grignard reagent, and it creates this intermediate that has the first time it attacks, it recreates a carbonyl. The second time it reacts, it creates a magnesium salt. Then we have to hit it with a little bit of acid. And what we end up doing is we're adding 2 equivalents of our Grignard to the system. All right, let me erase that so we can look at it again. Okay, so we can use any Grignard right here. If we use 2 equivalents of it, we're going to add 1 to the carbonyl first and then another to the carbonyl. And if we have the formate, notice there's a aldehyde at the end here, we can get a secondary alcohol out of it. However, if we're using a regular ester with a carboxylic acid and a regular alcohol, what we're going to end up with is a tertiary alcohol, because we already had an R group on our carboxylic acid, and then we're adding 1-for-1 equivalent of Grignard and 1 for the second equivalent of Grignard, okay? You cannot stop halfway through this. You will get a mixture of products. You must have 2 equivalents of Grignards, and they'll react until all the carbonyls are gone. So in the case of the formate esters, where we have the hydrogen here, we get our secondary alcohols. In the case of all of our other esters that have R groups on them, we'll get our tertiary alcohols. Okay, so the way this works, the reason you can't stop it is because part of the intermediate it happens, okay? And so I want to show that to you step by step. So the first step, of course, is the idea that we have that negative charge on our carbon right here. And those electrons are going to go ahead and attack our partially positive carbonyl here, giving us our first intermediate here. And this is a nice tetrahedral structure. We have a charge on oxygen here, and the magnesium salt is counterbalancing that charge. And so that's the first step of the reaction here. But now we actually can have a pretty decent leaving group by, let's see, having the electrons from this salt come in, recreating our carbonyl compound, and then kicking the alcohol out as a salt, okay? So it's kicking the alcohol out as the salt and leaving us with a ketone here. But now our ketone has a partially positive center again. It has a carbonyl again. Because there's still a carbonyl, that means that can be attacked by more Grignards or more other nucleophiles. Okay, now notice we do have a nucleophile in our methanol right here, okay? So if we look at that versus our magnesium, our Grignard reagent here, this one is much more nucleophilic because it has a much stronger base than this. So even if this did go ahead and react and go back to this, it would be a reversible reaction. So we're not worried about that reaction. Okay. But now we have our carbonyl. So what's the next step? The next step is to have that carbonyl react with the second equivalent of the Grignard reagent, giving us our intermediate tetrahedral structure again. And of course, when we acidify, we'll gain back our proton on our alcohol here. Okay, so that will be our last step in this reaction, is to have anything in the solution. In this case, we're looking at our protonated water as our source of our proton. So this is our Lewis base, grabbing the hydrogen, giving us our neutral tertiary alcohol. Okay, so that's the step-by-step reasons on why when we react those esters with Grignard reagents, they displace and go to the secondary alcohols for formates and tertiary alcohols for all other esters. Okay, now, before we go any further, okay, can we do this same reaction on a carboxylic acid? And the answer to that is no. because the carboxylic acid has an acidic proton. That acidic proton will react immediately with the Grignard reagent, that negative charge on carbon, to give us a neutral species, and therefore it will just eliminate the reaction and we'll have a salt. So this only works with esters, okay? So the Grignard reagents are only work with esters. That's very important to write down. Okay, so then our next reaction we can do is we can take our ester and reduce it down to an alcohol, okay? So if we have our carbonyl compound right here, remember our lithium aluminum hydride has our active species is our negatively charged hydrogen here. And what it's going to end up doing is it's going to be adding 2 hydrogens to the carbonyl and then taking away, not that one, taking away this in the process. So we're going to reduce down our carbonyl, but we always get a alcohol from the carboxylic acid portion, and we regenerate the alcohol that was the ester portion. So this was the ester portion here, and let me change colors. This is the carboxylic acid portion. So whenever we reduce down esters with lithium aluminum hydride, we end up with 2 alcohols, okay? The carboxylic acid is now an alcohol, and the alcohol is regained. All right, so notice I used lithium aluminum hydride there. Sodium borohydride is not strong enough to reduce down esters. So if we want to just react this side here, we get to use sodium borohydride right here. But if we wanted to reduce down this functionality and this functionality, we have to use lithium aluminum hydride, okay? So this is another case where we use a stronger reagent to reduce down a harder material, and we can use a weaker reagent to be selective about which carbonyl we want to attack, okay? So if we were to use lithium aluminum hydride, our final product would actually be OH. Oops, where'd it go? There we go. Our carbonyl up here is going to turn into an OH as well. So we're going to have a diol plus our, that's an H. Let me redraw. All right. We're going to end up with, I'm going to draw the LAH one down here. We get our alcohol because the carbonyl also reduces down, but our ester is going to reduce down, giving us this alcohol plus this section over here, alcohol. So with L lithium aluminum hydride, we'll actually get a different product. Okay, so selectivity here is the key. All right. So that being said, the last reaction I want to show you is the idea that the lithium aluminum hydride, not only does it reduce down esters to get you down to an alcohol, but it'll also reduce down the amide, okay? So in this case, it only reduces down the carbonyl. It doesn't clip the nitrogen off. That nitrogen carbon bond is strong, and therefore it does not clip that off. And so what we end up doing is just adding hydrogen to our carbonyl here, so that we end up with a primary amide gives us a primary amine. And if we have a tertiary amide, like we have here, see we have 1, 2, 3 things bonded to the nitrogen, that gives us a tertiary amine by reducing down just the carbonyl. And again, we have to use that lithium aluminum hydride for this, okay? That will reduce down esters and amides. Okay, so those are the primary reactions we have here in the carboxylic acid derivatives. We can convert higher carboxylic acid derivatives to like more reactive carboxylic acid derivatives like acid chlorides and anhydrides to esters and amides. And once we have esters and amides, we can use a selective reagent to reduce down that carbonyl of lithium aluminum hydride to give us alcohols and amines. Okay, so that is the conclusion for the goals, chapter 4, goals 3. If you have any questions while I'm switching over to the number 3, go ahead and type them into the chamber there. All right, we have,
Question.
yes.
So amides are always an ester or have a carbonyl group attached to it?
Amines or esters?
Amides, A-M-I-D-E.
Okay. Amides, yeah. Yeah, I might have accidentally said amine. I meant amide. A-M-I-D-E is an amide. Amides always have nitrogen. Okay. Esters always have we're made with an alcohol, and it's 2 oxygens bonded to carbon. Okay. An acid chloride is just the 1 carbonyl plus a chloride. An ester is 1 carbonyl plus COC bond. And the amide is okay, so let me go to here. So this also shows that right here. So let me clarify there. So right up here at the top, when we have the carbonyl plus a chloride, those are always acid chlorides. A carbonyl plus a carboxylic acid group, that's an anhydride. A carbonyl plus an OR group is an ester. A carbonyl with an OH group is the carboxylic acid. A carbonyl with the nitrogen is the amide. And then this is the carboxylate salt at the end. Does that clarify?
Yes, it does. So amides always have a carbonyl group. Amines do not.
Correct. If there's a carbonyl bonded to a nitrogen, that is an amide with a D. If it's just an R group with an amine, with a nitrogen here, that's an amine with an N. Amine, and D has a carbonyl group. Okay?
Thank you.
So I'm sorry if that wasn't clear in my speaking. But yeah, amines with an N has no carbonyl. Amide with a D has a carbonyl. Okay?
Thank you.
All right, great. All right, let's move on to the last one. Now, the whole reason that these have different strengths or different reactions based on ones that will react with with more reactive species and ones that are less reactive, like the whole reason the chloride's the most reactive and the amide's the least reactive, has everything to do with the basicity of the leaving group. Okay, remember, we are attacking some carboxylic acid derivative with a Lewis base, right? That's how we make the other derivatives. So let's look at base strength as telling us which can happen. So remember, in all these cases, we have a nucleophile that has electrons on it and comes in and attacks and displaces whatever this group is. If it's an acid chloride, that Y is a chloride. If it's an ester, that Y is an alkoxide or a salt of an alcohol. So this is the first step in all of these reactions here. That being said, the weaker the base that is produced, the better a leaving group it is, okay? So if we think about to our nucleophilic strength or our base strengths, when we were looking at substitution reactions a few chapters ago, we saw that our halides were pretty good leaving groups. That was one of the first leaving groups we ever had because they have very weak Lewis bases because they were very strong Lewis acids, right? So our HCl is a very strong acid, which makes our conjugate base, our chloride ion, a very weak base. Remember, acid and conjugate bases are opposite each other. So because this is so strong, that makes this very weak, okay? Now let's go over here and look at this side right here. Remember, when we looked at nucleophilic strength, our nitrogens with negative charge on them were the strongest nucleophiles because they were the strongest bases we had, okay? Because they're such strong bases, that makes them very weak acids, which makes them very bad leaving groups, okay? So that's why we can react from an acid chloride to an anhydride to an ester to the amide, but not go the other direction, okay? So think about it that way. The stronger the base is, the harder it is to get to leave. Therefore, the opposite, so that means the acid chloride is the weakest conjugate base, easiest to leave. This carboxylic acid, if we protonated it, would be more acidic than our alcohol. And if we had our alcohol, it would be more acidic than our amine, okay? So think of increasing base strength makes it harder to leave. Okay, so let's take that and look at the actual functionalities we have. So that means that if this is a horrible leaving group, that's going to have the lowest reactivity in the set. And if the alcohol is the next worst leaving group, then it's a little more reactive than an amide, but less reactive than the anhydride. And it goes up to our most reactive species, which is the acid halide, okay? So that's why whenever we want to do something where we have a reaction that runs very quickly, the acid halide will allow you to create any of the other functional groups. And once you get to the amide, you are really, really stable because the nitrogen is such a poor leaving group. Okay. So let's look at how that kind of plays out in the presence of water. Okay. So a carboxylic acid in the presence of water just, has an equilibrium, right? It has a pKa. And so it'll slowly deprotonate and reprotonate and deprotonate, but it's not going to change the nature of that carboxylic acid. It's still going to be a carboxylic acid, although it will, be slightly dissociated in the water. Acid anhydrides and acid chlorides react with water. They both react with water because water is a Lewis base and can come in and displace the chloride, giving us a stronger acid and our carboxylic acid here. Okay. Now that we have that, chloride is not a strong enough base to displace the hydroxide. So see how that previous slide with the base strengths making it a better leaving group means it can't attack and form that next species, okay? So most of these carboxylic acids react very rapidly with just the moisture in the air. So you have to protect them from that, okay? The next thing up is our anhydrides, okay? And anhydrides react with water very readily. And as their name suggests, it's just 2 carboxylic acids minus water, minus 1 hydride. So by adding 1 hydride back, we'll generate 2 carboxylic acids right here. And now that we have these carboxylic acids, neither one of them is a good enough nucleophile to displace the hydroxide on the other. Therefore, the back reaction doesn't happen. Notice there is no equilibrium here, okay? So it has everything to do with the idea that the carboxylic acids now are not strong enough to displace water, okay? In the case of esters, esters can hydrolyze slowly in the absence of acid or base. However, by heating it with acid or base, you can catalyze the reaction. And in the case of a base, you're using a base to pull hydrogen off. In the case of the acid, you're helping protonate the species, making it a better leaving group, okay? So the idea for what we're gonna show here is that in the case of hydrolysis using an acid, our intermediate species gives us this protonated species right here because the oxygen will come in here to give us our initial species, which will have a negative charge on that carbonyl oxygen. That carbonyl oxygen is protonated by the solvent. If it's protonated by the solvent, that means we can also protonate here, here, or here to make one of those other groups leave. If it protonates down here where I'm drawing the green line now, that's going to take us forward to give us the alcohol. If it protonated either of these species here, that would just take us back to the starting material. So that's why it's an equilibrium reaction on both sides of this. And that's why acid catalysis is actually easier, because we can protonate the leaving species, making it a neutral leaving species, and that makes it faster. Okay, so again, the first step is to formation of attack by our nucleophile to generate our protonated species here, which then can be in equilibrium with this protonated water species. Now, if it does that, it'll just go back, okay? That's not really helping us any. But if you instead protonate the alcohol as well, once that alcohol is protonated, when it leaves as a neutral species, and you generate the carboxylic acid. Okay. All right, so the other way to hydrolyze esters is to use base. And this goes back to an old term called saponification. In the old days, they used to boil animal fats and vegetable fats with lye, which is sodium hydroxide or potassium hydroxide, and that would create soap. And so that's why saponification actually came from the actual making of soap. So what we do there is we use our base catalyzed in the presence of water, and it generates the carboxylic acid salt plus the alcohol, okay? We also use the same technique when you make biodiesel. They create the carboxylic acid salt and the glycerol, which they separate out, and then they reacidify. Okay, and the way this works is a little bit different. The way this works is, instead of having water act as the Lewis base, we now have a hydroxide. Our hydroxide can act as the Lewis base. And so it'll come in and interact to give us our charged species here. Now we have two choices. We can have it leave as hydroxide, or, which would be the reverse reaction here. This is not going to leave, because that would be leaving as a dianion, so we're not going to move that. But the other thing that can happen is this thing right here can leave as the alkoxide, okay? So, and that's in equilibrium. If those electrons kick out and leaves as an alkoxide, we'll generate the carboxylic acid plus the alcohol, the salt of the alcohol, okay? Now, when we look at those two compounds there, the carboxylic acid is more acidic than the salt of the alcohol. Therefore, it's going to convert itself to the carboxylic acid salt plus the neutral alcohol, okay? Remember that carboxylic acid proton is more acidic than an alcohol proton. So it's going to drive that reaction. Notice that this is not reversible reaction, to the salt plus the alcohol. And then at the end of the reaction, you go ahead and reprotonate your carboxylic acid. But it all had to do with the fact that we had a really good, but better leaving group in our alcohol salt than in our water. Okay, so the two major differences between the acid catalyzed and base catalyzed hydrolysis is that the acid is only needed in catalytic amounts, because you regenerate the acid at the end of the reaction, and you end up with equal amounts of the ester and the alcohol and the acid after the reaction. In base-promoted hydrolysis, or the saponification, we have to use one equivalent of base for every single equivalent of ester, okay? Because the base is consumed, we end up with a neutral alcohol and a carboxylic acid salt at the end of the reaction. Therefore, in the basic promoted hydrolysis, we have to use an entire equivalent of base, usually a little bit more, to get it to go. So acid is catalyzed, base is equimolar, okay? In the hydrolysis of an ester with aqueous acid, we tend to call that reversible, because if you take away some of the water or you add more of the alcohol, you can drive the reaction back and forth. In the base promoted system, once you make the carboxylate anion, it is done. Nothing else will happen. So acid is catalyzed and it is reversible,
base is promoted and requires an entire equivalent and is not reversible. Okay, so what's the reaction we can do with amines? We can actually hydrolyze amines down to, I'm going to stop mirroring and re-mirror. There we go, come on. There we go. All right, so what we're going to do here now is we've shown you that we can hydrolyze acid chlorides. We've shown you we can hydrolyze anhydrides. We showed you you can use acid or base hydrolysis to hydrolyze esters, okay? So amide is the last one, and amide most of the time requires either acid or base. And in the case of acid-based hydrolysis, you have to use an entire equivalent of acid, okay? An entire equivalent of acid, because once you displace your amine, you have to trap it as a salt. You need to make sure it is no longer a nucleophile. So when you hydrolyze an amide, you must use an entire equivalent of acid, and it usually takes a lot of heat as well, okay? So in the case where you have acid right here, you'll end up with the carboxylic acid and your amine as your acid salt. Okay. So it is really takes a lot of acid and a lot of heat to get this to happen. Unlike the ester, which is only catalytic acid and a little bit of heat. Okay, so that being said, we can hydrolyze any amide using a very strong base and water and heat, and it gives us time to make it. So, we can also hydrolyze with base. And the way that works is the idea that the OH, the hydroxide, comes in as our nucleophile again, and then once the amine leaves as a neutral species, right, we form the carboxylate salt, okay? Now that we have that carboxylate salt, the amine is not a strong enough base to attack the carboxylate salt. Therefore, we have to use an entire equivalent of base to do it, but it generates our free amine and our salt, neither of which can react with each other. Excuse me. I thought I got rid of my cough today. Oh well. All right. So in summary, all of the functional groups of carboxylic acid can react with water. However, in the presence of the acid chloride and the anhydride, these spontaneously happen and do not require heat, and you can use just like humidity from the air to do the reactions. Once you get to the ester, you have to use either acid or base to promote the reaction. In the case of acid, it's catalytic. You only need a drop of acid to and a little bit of water to be able to drive it to completion there. Okay, my iPad is no longer sharing again. There we go. In the case of the ester, if we have an acid here, we can use catalytic acid because we'll generate a free acid in the back of the system. In the case of base, we have to use at least one equivalent of base because we form the salt. In the case of the amide, we have to use one equivalent of base because we need to form the salt and the free amine. And in the case of acid catalyzed, we actually have to use at least one equivalent because the amine will be trapped as the acid salt and the carboxylic acid will be free by itself. Okay, so only this is catalytic. Oops, sorry. So only this is catalytic. The rest have to use entire equivalents to get it to happen. All right, so this summarizes, this finishes out our chapter 14, 13 goals, stability as a function of basicity. And I hope you see that these hydrolysis reactions are dominated by that basicity of the leaving group. Okay, any questions on that?
Okay. I'm going to stop sharing here. I'm also going to stop recording.